For a summary of today's proceeding, we have Professor Carlos Frenk, who will do this for us. Thank you.
I will keep that to the end, and you may not want to clap. So let me just start with a disclaimer. I am a cosmologist. I define myself as a hardcore cosmologist. So my world is a world of equations, supercomputers, and data. That's what I get paid to do. I don't get paid to think about what was there before the universe, whether God made the Big Bang, to think about time, whether it exists or not, whether reality. I don't get paid to do that. And I must say, I'm very jealous of our colleagues like Matt, Adam, and Alistair, who actually get paid to think about that kind of stuff. So I feel very jealous that you can do that for a living. Now, I would never dream of thinking about these kind of issues during working hours. And then I realized today's Saturday. So I can talk a little bit about that kind of stuff. Now, Joe asked me to give a summary. I already knew that my philosophy colleagues and historian colleagues are immensely articulate and clear, and I wouldn't dare try to do a summary of what they said so beautifully and elegantly. So I'm not going to give a summary as such. What I'm going to try to do is just give you a perspective, put things in a slightly wider context, with reference to what we heard today, which was really a set of wonderful, fascinating, and truly enlightening talks. So the first thing we heard today were about the 400 questions that Edward Grant talked about. Now, what struck me about these 400 questions is that many of them are very similar to the questions that cosmologists ask today. So here's a slide I give in public talks, and you see the questions that we ask in cosmology today are exactly the same that were being asked 400 or 500 years and more. How did the universe begin? What is it made of? How did it get to be the way it is? And what does the future hold? Now, of course, Adam mentioned about modern cosmology being a scientific topic. And indeed, it is a scientific topic. It's based on the laws of physics. And that is very restrictive. So we have a certain domain in which we can work. And it's restrictive, but it's also, as we will see, very powerful. Now, it's based, cosmology, on the laws of physics that are experimentally discovered and verified on Earth. Now, for some reason, and here I was disappointed that the philosophers didn't come back to this. So it appears like as though the laws of physics that we discovered here on Earth in the laboratory apply not just here, but apply everywhere in the universe at all times and in all places where conditions were completely different to the ones here. So one of the things that I have always been mystified by is the universal or seemingly universal nature of the laws of physics. So maybe, Matt, next time I hear you, maybe you could talk about this. I was disappointed to see that's not a topic that was covered. Now, so modern cosmology is based actually on two revolutionary ideas from the early 1980s. The idea of cosmic inflation, we've heard it mentioned several times, and the idea of dark matter being some form of elementary particle. So there's these two revolutionary ideas and two technological advances. One, and I will show you some examples of both, new detectors and telescopes, many of them in space, and the other one, supercomputers and simulation techniques. So I would like to tell you a little bit about the context in which all these questions about the origin of the universe, time, and so on are placed. So I want to spend a little bit of time telling you about this lambda CDM model that was mentioned several times today. So, and why this is such a impressive construct. So, cosmic inflation, as I will show you, gives you the initial conditions for the formation of structure in the universe. The dark matter is the mechanism that causes structure to grow. And simulations give us the ability to calculate how structure forms and evolves. And of course, telescopes give us the ability to test predictions from simulations. So you see the entire scientific method reflected on this. So cosmology, as we heard from Cora, is based on, and from many of the other speakers, based on the known laws of physics. I listed some of them here. And the key point, I think, which was not really emphasized today, is that having an understanding of the initial state, at least from the point of view of the formation of structure in the universe, understanding the laws of physics means that the theories we have today have predictive power. So we can make predictions, and because we can make predictions, we can test them against experiments. So we heard how the universe has a rather bizarre composition. This is ordinary matter. So ordinary, I even forgot to put the title, but and this is dark matter and dark energy. And the reality is that we have been able to construct a wonderful model of the universe without really knowing what 95% of it really is. We know the dark energy has to be there. We know the dark matter has to be there. We feel it. We measure its effects. But we don't yet know what these two things are. And if it's time for questions, I'll be very happy to answer questions as why are we so sure that this is what the universe contains? Now, we heard about inflation from several of the speakers this morning. I think Alistair mentioned it. So what is inflation? Well, inflation is the mechanism that set up the initial conditions for the formation of structure in the universe. Now, so we also heard about the Planck time. I think it was Alistair who mentioned the Planck time, which is the earliest time when known physics applies. So it's the time, and he didn't define what it is the time when uniquely in the history of the universe, gravitational and quantum forces were comparable. And in fact, here's the equation for those of you who are mathematically minded. The key point is a very early time, 10 to the minus 44 seconds. That's a decimal point, 43 seconds and a 1. That fraction, 43 zeros and a 1, that fraction of a second is the barrier to known physics. And yet, it's a very small number. So we can apply the laws of physics right up to that very initial state, below which, as I think Alistair also mentioned, we cannot really progress because we're lacking a theory of quantum gravity. A theory that, not for lack of trying, this is where many of us believe Einstein wasted most of his life trying to come up with a theory of quantum gravity, which is kind of difficult because he didn't believe in quantum physics anyway. But and others, Stephen Hawking, likewise, and they all failed. And maybe that's telling us something quite profound. So that's the very beginning. Luckily, the story of modern cosmology starts a lot later in this logarithmic space. Inflation didn't happen at the Planck time. It happened a lot later, 10 to the minus 35 seconds after the Big Bang. So according to the idea of inflation, and it sounds very weird when I tell you, it was mentioned many times during the lectures today, but nobody actually explained what it is. So let me tell you what inflation is. It's basically, or I think maybe Alistair tried in 2 sentences, but it's the universe after the Big Bang was born in a slightly unstable state characterized by something called vacuum energy, and which is the nothing that Matt was talking about. I think it was unfair to make fun of Lawrence Krauss, who used to be a friend of mine, but because what do we mean in physics by vacuum? We sort of try to emulate the philosophers and be elegant in our language, and we call it nothing. That's not really what we mean. The vacuum is a well-defined physical concept. In any case, at the beginning of the universe, there was some excess of vacuum energy, and the universe shook it off by expanding exponentially rapidly during a very brief period of time. And so we know this happened. I will tell you the evidence in a minute, but in the words of Martin Rees, who was mentioned at least once, if not twice, my mentor, he said, we know there was a bang, but we just don't know what went bang. So I think Alistair talked a bit about this in various ways, whether it was God who made it, or whether the universe, whether the question doesn't make sense. And the reality is that from my perspective, as a die-hard cosmologist, This is an interesting question, but one that I don't even try to answer on weekends, because I know that my tool, which is physics, breaks down before we can, in fact, even pose that question. So we know there was a bang, but we don't know what exactly went bang. Now, so I'm going to tell you the history of the visible universe in one slide. So as I said, the story begins early on, 10 to the minus 35 seconds after the Big Bang, when cosmic inflation happened. And cosmic inflation is driven by quantum phenomena, and in the quantum world, everything fluctuates. That's what the vacuum is about, and that's what the vacuum isn't really nothing. It's something, but it really is nothing because there's nothing in it. That's just language. In the vacuum, there are quantum fluctuations, and these quantum fluctuations get stretched when the universe expands exponentially fast. I have a movie, actually, that I stole from a Dutch particle physicist. Here's what the vacuum looks like. I agree. Who was it who talked about the vacuum? Was it Alistair or Matt? I agree it's not empty, but there's stuff going on in it. But what goes on in it are these fluctuations that come and go. However, they get stretched as the universe expands. And the outcome of that is that the universe gets seeded with small perturbations. And the amazing proposition of modern cosmology is that everything we see in the universe came out of these quantum fluctuations from inflation. Galaxies, stars, planets, ourselves, we all came out of these quantum fluctuations of inflation. Now, I know you're all thinking, God, this guy gets paid to do this kind of stuff. It sounds pretty incredible. It sounds like magical realism. I come from Latin America, from Mexico, where magical realism is something you live in every day. Although I left 50 years ago, but still, this really reminds me of stories by Borges or Fuentes or those kind of writers. And you see why this is different from that. So first of all, dark matter gets produced a little bit later, and the dark matter amplifies these quantum fluctuations and makes them grow a little bit. Now, the beauty of this is that we can mathematically calculate these processes. Here's a technical plot. I'm not going to describe it. Something called the power spectrum that Cora valiantly tried to explain. Doesn't matter what it is. All I want to illustrate here is that we can mathematically calculate the properties of these small perturbations. Now, but as I said, what the difference between this fantastic story I'm telling you about quantum fluctuations, inflation, and a Gabriel Garcia Marquez story, the difference is that you will never be able to go to Macondo and see if it's raining, but you will be able to test these ideas. So how do we do that? Well, we heard about the microwave background radiation. The early universe was hot and dense. As it expands, the radiation cools. And by the time the universe is about 350 or 80, as Cora said, 1,000 years old, the first hydrogen atoms form, and this radiation from the Big Bang is free to escape. And as I'm sure many of you know, this is the first light of the universe. It cools down as the universe expands. Today, the universe is so old that this radiation that was very hot, hotter than the sun, than the surface of the sun when it was emitted, is now cooled down to a mere 2.7 Kelvin, 2.7 degrees above absolute zero. So it's very cold. It's in the region of microwaves. And those microwaves were discovered by these two gentlemen in the 1960s, Arno Pensaya and Bob Wilson. And of course, they had actually discovered the Big Bang. They discovered the radiation, the heat left over from this hot early phase. And of course, they got the Nobel Prize for that. And this is the cosmic microwave background radiation that several of the speakers today mentioned. And the great thing is that it brings us news about the properties of the universe at this very early time. The other thing is that we can mathematically calculate, and Cora showed some examples, the properties of this pattern of hot and cold spots in the temperature due to these perturbations. In fact, 1992 was the turning point in modern cosmology. This glorious map of the temperature of the radiation. This is a map around us, but projected onto the screen. that showed that this heat left over from the Big Bang is not uniform. It's characterized by hot and cold spots. This discovery made headline news. I think I see lots of people with gray hair. You remember this great newspaper, The Independent, that was now doesn't exist. Now, I'm going to leave modesty aside, if you forgive me for a second, because I did make a contribution to this, which is described here. And it says, Carlos Frenk, an astronomer at Durham University, said yesterday, "Oh, wow, you can have no idea how exciting this is." That was my contribution. To this, my contribution to cosmology. But the one thing that's clear, my wife knows that my epitaph will be, "Oh, wow." And let me tell you why it is a wow moment. Now, just before that, this got my friend George the Nobel Prize in 2016. The radiation was remeasured a decade later with better resolution. And finally, the map that Cora showed, and I think another of the earlier speakers also showed, the Planck map, the definitive map of the temperature, anisotropies, as we call them. It's just a map of the temperature of the heat left over from the Big Bang. Now, if you believe the Macondo story that I've been telling you, you're actually looking here at quantum fluctuations from inflation. And that's what it is. So this is your one chance to see quantum fluctuations. And not any quantum fluctuations, the quantum fluctuations that gave rise to our universe. Now, here's another plot I'm not going to describe. I think Cora did a brilliant job of explaining the so-called acoustic peaks. This is, again, a mathematical description of that pattern that I just showed you. What I want to show you, the reason I'm showing you this, is that these calculations were done 42 years ago. In fact, Stathu was a professor here for a long time. People got the Nobel Prize in physics a couple of years ago. So these predictions existed 40 years ago. And Cora showed this incredible plot that compares the predictions in green to the measurements in red. Now, this is the oh wow. And this, to me, is the most wonderful picture I've ever seen. Considering I'm an art lover, I go all over the world to look at Rembrandt pictures, and not just Rembrandt. I can give you a whole lecture on other pictures. To me, this competes with that. In a way, it's better, because Rembrandt was just one guy. This is the work of thousands of scientists. And physics doesn't get any better than that. The fact that we can predict, for some reason, the species. It's a question here for Alistair and Matt. Why is it that the species of creature evolved in this corner of a galaxy, capable, on the one hand, of calculating mathematically, quantitatively, the properties of how the universe began, and this same species is also capable of building machines that they hurl out of their planet that can measure, as Cora said, the signals which are 1 part in 100,000. So to me, that is a mystery. And it lays the groundwork. So this is why I think cosmologists all are convinced that there is truth to this model. At some level. It cannot be the whole picture, and I will tell you in a minute why not. But this is the way it is. So how do galaxies form from here? Well, the rest really, although I spent my whole career doing this, going from here to there. Well, I started before this was known, but still, it's kind of mundane, grinding, solving equations. And the way we do this is that we know we use computers. We know the initial state. We know the initial conditions. I just told you about those. We make some assumption about whether the universe contains cold dark matter, dark energy, etc. And we just solve equations, from most of them from the 19th century. Simple. And you program a computer, which is very rewarding, because computers work on weekends, and they don't answer back like students do. They just do their job, and you go and see what comes out of them. And I'm going to show you first what you would see if you were able to don dark matter glasses and were able to travel at much faster than the speed of light. This is how the distribution of dark matter ends up being today, with this richness of structure, all coming from these very simple quantum fluctuations from inflation. Now, nowadays, we can actually do simulations, not just of the dark matter, but also of the ordinary matter. So you're going to see what comes out of that simulation done in my institute. And here's the dark matter becoming increasingly clustered, as Cora showed, increasingly interesting. And now we're going to cut in a minute to gas that you can see here. The gas realizes this gravity. There are lumps in the dark matter, feels the gravity, falls into these lumps, and because it's spinning, then it settles into the structures that we will see evolving. And you can see all these things, we call them mergers, lumps coming together on the reaction of gravity. And the bigger the lump gets, the more its gravity, so the more it attracts other things. And these are now stars that form in this program where we can include astrophysics and calculate the formation of stars and quasars, black holes, everything is in here. It's really a magical world that I live in, which is wonderful. So here is what comes out of our computer simulations, and I will pan out in a second to see that this is happening not just here, it happens everywhere in the universe. So stars again. And this was quite an accomplishment to get a thin disk of stars out of a computer. It was quite, whenever these kind of calculations take 10, 15 years to get the ideas running, and then maybe a year or two to do the simulation. Now, so here are some images, and many of you who like to look at catalogs of galaxies might wonder which catalog did this come from. I like to tease Roger and say, do you think this came from the Hubble or the Baculor's catalog? No, they came out of my computer. And you can see we can do a wonderful job reproducing the universe today. So where are we in cosmology? We have this lambda CDM model that accounts for a huge range of observational data from the Big Bang to the present. It has its weaknesses, and there's still work for future generations to do, because we do not really know exactly what the dark matter is. We think it's an elementary particle, but it's yet to be discovered, and we don't know what the dark energy is. Now, these are very important questions. There are many people spending a lot of money trying to find dark matter. These experiments usually take place in mines or at the bottom of, mines. There's one, used to be one in the UK. Ian Corbett, if he's still here, he used to be one of the high people in the Research Council. He knows all about the dark matter experiment that we had in the UK. Fortunately, it closed down, so these experiments are now in Canada, that one, in China, that one, but no dark matter has been detected yet. So I want to finish off by telling you about this mysterious thing called the dark energy. It's the domain of observational astronomy. What is the dark energy? Well, we don't know. It has to do with Matt's nothingness. It probably has to do with the vacuum. But the problem is, if we try to predict the value of the cosmological constant, we get the answer wrong, not by a little bit, but by a factor of 10 to the 120. So that's the calculation. It's very simple. You can see I can do it in 2 lines. So this turns out to be 120 times wrong, 10 to the 120 times wrong. And some people call this the most inaccurate prediction in physics ever. So we know our cosmology is incomplete, and that's just wonderful. There's still work to be done. Now, how are we going to try to make progress with this? Well, we have this plethora of instruments, and we've already heard people talk about this one from the questions, and Cora talked about that one. And in fact, I talked also about DESI. Here is a picture of DESI made by one of my students, whose name, unfortunately, has disappeared here. In any case, so she explained this amazing survey, which is a leap forward in trying to understand our universe. DESI stands for Dark Energy Survey Instrument. So we just published our data. There was a big splash in April, and Cora showed some results, but I'm glad she didn't scoop me completely because she didn't show what to me is the most exciting one, and that's this one. So again, technical details don't matter. These are the measurements, different kinds of measurements. These are called probability ellipses, and the best value is here, and these are with 95%. There's only a 5% chance that the truth lies outside these contours. Now, lambda CDM is here. So lambda CDM is ruled out by this DESI data. Still not completely ruled out. These are still early days. There are probabilistic statements, but at face value, our cosmological model conflicts with the data. And interestingly, the way, if this was the truth, and we will have to confirm this, it has huge implications for the future of our world. And I was on the Today program talking about this, and I got hundreds of emails about one sentence I said, which was, this opens up the possibility that a future of the universe may not be as boring as, who was it, Alistair implied. So let me just finish off with a couple of slides telling you about the end of the world. So the long-range future of the universe depends entirely on the nature of the dark energy. There are three possibilities. We have a big crunch, indefinite expansion, or something called the big rip. Now, so these are the size of the universe, a function of time, and the lambda CDM model is this line. It's for a constant lambda, which is Einstein's cosmological constant. And this is really boring because it's a universe that expands forever. And all the wonderful things that I can't remember now, it was Matt, or Alice, I think it was Matt, all these wonderful things he talked about, Everett's the preserver of quantum mechanics, it was him, giving a talk somewhere else, but wearing my shirt instead of his shirt. This would all happen in that universe. So I find that kind of annoying and sort of inconvenient if there is someone else and Roger is giving my talk and I'm sitting there. I don't quite like that. So, but this is what the standard lambda CDM model tells you. The new DESI measurements, interestingly, if you take them seriously, which you shouldn't yet, it's early days, fall in this line. So this is the big crunch. That was just my way of representing Einstein's cosmological constant. This is marginally inconsistent with DESI. This is what the picture seems to be indicated if these very preliminary measurements are correct. And I stress, bring me here next year, and then these may have all gone, and we will be back to the boring universe. So why people prefer a big crunch? I know Roger Penrose likes it. Many people, I don't know what people here feel, the philosophers, when I talk to philosophers, somehow have more sympathy for this. Certainly avoids this problem of Roger being here giving my talk. I don't know what to make of this. This is an animation of what the big crunch would look like. And now you can tell me if really you'd like to live in a universe which in the fullness of time is going to do that. I don't know. In any case, I heard about the string theory landscape, which might explain these the fine-tuning. I couldn't resist to showing you a picture of what it looks like. We had a wonderful description about valleys and so on. Well, here's what it looks like, and I disagree. Oh, and actually, as I think Matt stressed, this is a natural consequence of inflation, by the way. The most current theories of inflation, he mentioned Andre Linde's eternal inflation. This is exactly what you would expect. And a landscape of universes, and he explained very coherently, you wander around, and then the universe falls into one of these valleys, and then it's stuck with a cosmological constant, or all sorts of ugly things like that. So then let me just then finish off with the statement that cosmology is a branch of physics. Its goal is to gain knowledge about our universe. It's limited by the restrictions of the scientific method, but as I hope I show you, it's a very powerful way to learn about our world. And the future, well, I showed a picture of these wonderful instruments. And as we saw today in these marvelous talks by everybody who spoke here before me, including Alistair, who we had a double dose of him. And at first I was slightly skeptical. Well, I can put up with 1 hour of Alistair, but I had to put up with 2. And after 2, I was looking forward to the third. But there wasn't a third. Instead, we got Matt, who also gave a wonderful, absolutely fantastic lecture, following, of course, Adam's wonderful review of the history of cosmology, and finishing with my colleague, former Geordie Cora Ullman. So here's where we are. with instruments, technology, but above all, with the ability to enhance a human brain with the power of these machines. My computer in Durham is already capable of doing more arithmetic operations per second than a human can. So the future is pretty unlimited, and I look forward to listening to my philosophy colleagues, how they absorb all the deluge of data, information, and analysis that's coming in the next few years. And I'll stop here.
Very much for this super exciting talk. In fact, it's a summary, so everything that was before was also super exciting. So I think we have finished for today. I hope everybody enjoyed and goes home with a lot of thinking about. Thank you.